How about now? Sounds better. All right. So my name is Axel Liljencrantz. I'm a dog person. And here is what I will be talking about today. I will be talking a little bit about the company I work for as an introduction to what we are doing. Then I will be talking about compactions, how they work, and what that means with regards to how you should design your data structures in Cassandra. And I will round off my talk by talking a little bit about how the future looks when it comes to storage. All right, so how many people here have actually heard of Spotify? Raise your hands, please. Okay, so some people, but not all of you, not by far. Spotify is probably more well known in countries where it actually exists, unlike Russia, but it is a streaming music service. Basically, you have a library of about 20 million songs, pretty much all the music out there, and you can listen to any song at any point where you like. You have an offline mode, so you can listen on your airplane. You can create your own playlists, you can share stuff, and blah, 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 all that boring social crap. I don't actually like people, so I don't want to do that. Anyway, we have about 24 million active users, and so far we have generated roughly $1 billion in revenue for artists and the record industry. So those numbers are, I guess, either pretty big seeming or pathetic, depending on if you are Google or not. Anyhow, our service obviously needs a backend to store all those songs and all those playlists and whatnot. And it consists of roughly 6,000 servers at the moment. Split out over 4 different data centers all over the world. The backend is separated into roughly 100 different services. Services that are mostly written in either Java or Python, but we have some things written in C++, we have some Go, we have some PHP and so on, but mostly a Python and Java shell. This very heterogeneous thing, we also have very many different storage solutions. For instance, Cassandra, which you may have heard of, or Postgres, Tokyo Tyrant, Sparky, SQLite, and so on. The design here is basically meant to be something where any single service should be, if we decide this is not good enough, it should be small enough that we can take the service, rip it out, and replace it with something else in the course of a few weeks or a month or so. That's not entirely true, because there are several services that are much, much larger than that and more complicated, but for the most part, this is actually kind of true. And this kind of very distributed architecture has suited us very well. It also allows us to work in very small and independent teams, so that we don't have a big central structure of people who made us designing everything. We work independently, which allows us to move relatively quickly. But obviously, I'm not here to talk to you guys so much about, say, Postgres today. I am here to talk about Cassandra and how we use it at Spotify and other things like that. To be honest, we kind of got off to a bumpy start with Cassandra. We had the playlist system, which is something where we store roughly 1 billion different playlists that users have created. And some of these playlists contain many, many, many thousands of items. We had tried to create our own storage solution to store these playlists, and it was a complete and miserable failure. So we decided to try something else, and what better idea than to take our biggest, heaviest used and most critical piece of data infrastructure and use that as the test bed for a brand new unproven storage component, right? Right, awesome. So that didn't go very well, but we spent a couple of, well, probably by now, a few man-years fixing the problems created by not understanding Cassandra well enough to implement the right data structures, and by now we're actually in a pretty good place with Playlist, and it works very well. But there were a lot of lessons down the road. Hopefully I can make sure you don't repeat all of our mistakes. Mostly our problems have been in relation to performance. They have never ever been in relation to data loss. We have had many outages, we have had many problems along the way. We have never lost as much as a single bit of actual data, which I think is actually a very impressive property. The basic gist of what I will be telling you is that if you actually don't know what you're doing and just hammering away at what sounds useful with Cassandra, you will not have very good scalability. And this is to a degree different from old school relational databases, which for all of their bad properties when it comes to handling big data, they are actually kind of forgiving in that they have had so many man-years of optimization work poured into them that it's kind of impressive the retarded stuff that you can throw at a relational database and it will actually survive somehow. Okay, so what does our Cassandra infrastructure look like? I checked last night and we have 47 different clusters up and running. The largest of our clusters at the moment is available in 2 data centers with 30 nodes in each data center. It has around 300 or 400 gigabytes per node, so something like that, yeah. 10 or 20 terabytes, I think, of data in that particular cluster. We are, for as many of our clusters as possible, using Fusion IO PCI cards. Has anyone here heard of like the PCI Express flash cards? Does anyone here use them? Not a lot of people. I will be spending some time talking about them because they are freakishly cool. Basically, the performance difference between rotating Rust hard drive and an SSD is kind of comparable to the performance difference between a regular SSD and a PCI Express card like this, which is kind of useful, but on the negative side, they cost probably as much as you and I make in a year, which is a bit of a bummer. Anyway, these cards have very desirable performance characteristics. Our most heavily loaded cluster sees 5,000 requests per second to just 3 nodes at peaks and a sustained rate of maybe 1,000 requests per second. And during these peaks, we will be using roughly 2% of all our available IOPS. So IOP scalability is simply no longer a factor with new cool flash technology. But first, let's talk about compactions. I was told that most of you guys would be pretty technical and already reasonably heavy Cassandra users. For you guys, you should have no problem keeping up with what I'm saying. If there are a bunch of Cassandra newbies out there, you still get to listen to the smooth and pleasant baritone of my voice. So in the end, we're all winners. But let's talk about compactions. A compaction is the act of taking a bunch of SS tables and turning them into a bunch of other SS tables. And while doing so, removing any unneeded data. that can be overwritten data, and you can also, in some situations, remove tombstones, though, as I will mention later on, not as often as you would like. The main reason for compactions is to reduce fragmentation. If you take 10 different SS tables that all have the same row stored in that SS table, hopefully the output of the compaction will only have that row stored in one single place, so that you will not need to do 10 seeks but only one in order to read that particular row, which is usually very useful. So that's the basic idea behind the compaction, but then they vary very much in details. There are three main types of compactions, I guess you could say. The first one, the simplest one, is the major compaction. It is just take all of the SS tables that you have belonging to the same column family and turn them into one huge mega SS table. And this is something that you have to do manually. It is not an automatic thing, and it's very rarely something that you actually want to do because it's prohibitively, I think that's how it's pronounced, it's a very hard word for me, expensive operation. So you usually don't want to do that. The next thing you can do is something called a sized tier compaction, which is basically you take 4 SS tables, you try and locate 4 SS tables that have roughly the same size, and you turn them into one SS table that will be roughly 4 as large. That's it. That's not a very advanced or useful logic. It has the advantage that you don't perform that many compactions, so it will be super fast, and it has a bunch of disadvantages though. For one thing, it requires huge amounts of free disk space, because you will end up in a situation occasionally where pretty much all of the data is located in 4 very large SS tables. And if Cassandra decides that, okay, so I'm going to now take 4 largest SS tables and turn them into one, then you will temporarily, while the compaction is going on, double the disk usage. So you always need to use less than 50% of your hard drive. That's not really a big issue in my opinion, unless maybe you're very resource constrained and using SSDs and can't really afford them, because disk space is kind of cheap. But it's still something that you need to know about. A more important problem with size tier compaction is that rows can be very, very badly fragmented. Basically, if you keep writing to the same row over and over and over again, for a very long period of time, what will happen in the end is that that row will exist in every SS table on your disk. And once you have like 30 or 40 or 50 or even 100 SS tables that you need to read from whenever you're going to do a slice operation, you're not going to have a very good time. So there are a lot of improvements that have been done over time to size tier compaction. So there are a bunch of use cases where it's actually useful. One of the latest of these is issue Cassandra 5515, which will basically mean do an analysis of usage of SS tables, and it will, for all SS tables that are no longer read from, it will stop trying to compact them. This will take the already great write performance of size tier compaction and make it even better, while doing nothing for the usually not very good read performance. But there are some suitable use cases for size tier compaction. Jonathan mentioned before that time series data is a good fit for Cassandra, and they have done various optimizations that mean that time series data can not only be written but also read very efficiently using size tier compaction, which is very useful. Basically, specifically in the case where you're writing with a more or less monotonically increasing key for instance, a timestamp, you can do very efficient slice operations, even if a single row exists across all SS tables. I'm not going to get into the details of that, because then I'm here all day, but overall, if you are extremely write-heavy, then size-clear compaction is also a good idea. And if any given row will only be written for a very short period of time, like clock time, then that is also a good fit for size-clear compaction. But still, it has a lot of situations where it's not very scalable. Like they said, if a given row is frequently written to, it will end up in, well, not all necessarily, but at least the vast majority of all of your SS tables, which is not all that much fun. And this is actually a write pattern that we will see a lot of the time. Nearly all user-generated content is spread out very skewed. So there will always be some users that are super productive, that output a lot of stuff, and they will also frequently be the ones that are popular, that people read from, and so on. And also, most batch processed data end up writing the same columns every night or every week or whatever. So that is also usually something that is not very suitable to size-clear compaction. You need to do the analysis and figure this out for your specific workload, but as rules of thumb, both of these are not things that are going to be very suitable to size-clear compaction. I said before that there are 3 compaction filter strategies, and I mentioned 2 already, so there's a third one, and hopefully it will be awesome and fix all of these problems, right? Yes. So let's move on to that one. The third compaction strategy is something called level compaction. Like so much else that is good and beautiful here in life, it was invented by Google. It comes from a product they have called LevelDB, which they released to the open source community in 2011. And it's pretty much a SS table sharding mechanism. I'm going to start off by talking about how the data, how the different SS tables will look on disk to give you an idea about what the layout is. And after that, we will talk a little bit about what that means for performance. And finally, we will move into the interesting part, how the compactions actually make these constraints come true. But the first things first. In level compaction, you divide the world into multiple levels called level 0, level 1, level 2, level 3, and so on, which I will try to illustrate here. So can I press something? There, L1, and so on. And every single level will contain SS tables. Specifically, level n will contain 10 to the power of n SS tables. So in level 0, we have just the one SS table. Level 1, we have 10. Level 2, we will have 100, which, and so on. And level 6 here will probably extend all the way to Vladivostok. So these millions and millions of SS tables, that just sounds like there's more places to put stuff and more fragmentation and more seeks. Not so though, because the row key domain is partitioned within a level. What that means is that in level 0, you only have one SS table and it can contain any row key. But in level 1, we have 10 tables, and the first one will contain all of the keys, beginning with an A or an B. The second key will contain all the C's and D's and so on. So that what this means is that whenever you do a read, you will at most have to read from one SS table in every level, right? Because you know the row key, so that row key can only live in one SS table. That's super convenient. So how many levels are we going to end up with? Well, it's usually not a very good idea to have more than half or 1 or so terabytes of data on your disk. And with 5 megabyte SS tables, I actually forgot to mention this here. This is also kind of important. All of the SS tables in level compaction have roughly the same size, fixed size that you configure and set. I want the target size of my SS table to be 5 megabyte or 50 megabyte or something like that. And if we're using 5 megabyte SS tables, we will end up with 6 levels to store half a terabyte of data. That's not a lot of SS tables to end up with in the worst case. So the worst case performance with 6 seeks or so to do some kind of super heavy slice of very unfortunately stored row, that's not too bad. And even nicer is that in practice, pretty much all of the rows except for the lowest one will not have that much data in it. There's some kind of calculation that tells us that in theory, with some arbitrary assumptions, we should get something like 90% of all reads being satisfied by just checking a single SS table. In practice, we have not found that to be true, probably because real data tends to be very skewed, that there are some rows that will be written to way more often than others, and those rows will also be read from way more often, and they will probably have slightly worse characteristics than the average table. So what we have found in a production environment is that depending on how your data looks, between 50 and 80% of all reads only touch a single SS table, and so only perform one disk, unless it's in the page cache or something, in which case it will be 0 seeks, of course. But still, that's a pretty good performance profile, I would say. So the question then is, how do we make these very desirable characteristics come true? How do we perform compactions? So let's go back to this look with the different levels and their partition keys. Say that we have added a new SS table to level 1 here. And don't worry about how that SS table appeared in level 1. We will get to that later, and it will hopefully be very clear to you in a bit. So let's just assume that suddenly there's an 11 SS table in level 1. Oh no, this is a violation of our constraints. This is so terrible. We have to do something about this. So what do? We pick one arbitrary SS table from the violating level, and then we also pick all of the overlapping SS tables in the next level. So we have one SS table here in level 1, and that will, the keys, the row keys in that SS table will be something like B to D, and that will be these keys here. And so all of the SS tables that contain keys that are overlapped with that table are also picked up. That will usually be roughly 10 more tables. So we will pick up roughly 11 tables here. And we'll take all of those tables and we will compact them together into a new series of tables. Doing all of them, like removing the overwritten data and partitioning them and blah, blah, blah. And whenever we hit the size boundary of our desired size of an SS table, we will do a split here, so that we will probably statistically end up with something like 11 brand new SS tables here. And then we will just remove all of the old SS tables, delete them from our world view, and instead insert the new, brand new blue 11 tables in the lower level to level 2 here. And what exactly did this accomplish? We have exactly the same data. The only change that's happened is that we have moved one SS table from level 1 to level 2. Some very unusual cases, theoretically, where you have a lot of data that's been overwritten, so that you only end up with 10 SS tables, but that's going to be very unusual. Pretty much always, you're going to end up with the same number of SS tables, but we have moved them one step down. And then we're just going to have a new layer violation in level 2 instead of level 1. And then we'll do another level compaction, where we move one SS table from level 2 to level 3. And then it will keep on bubbling down that way until we hit the final level, level 6 or 7 or whatever it happens to be for this particular column family. And when we hit the last level, that level is not going to be full, and so we're good. And of course, the undesirable thing here is that we're not going to perform one compaction here. Whenever our mem table overflows and we hit this, we're going to perform usually roughly the same number of compaction operations as there are levels, and so that's going to be something like 6 compactions, and it's going to involve something like 60 different SS tables, because we compact away 11 SS tables in each compaction package, something like that-ish. That's a lot of data. And in practice, level compaction will perform at least twice as much work doing compaction as size-tier compaction. So for very wide heavy loads, it will be noticeably slower. But in return, you get a much better read performance, and perhaps even more importantly, get a way less, you get a read performance that has much fewer, call it, bad edge cases. I'm looking for a different word, but I can't find it. Moving on. Anyway, at Spotify, in these 47 clusters with probably 100 or 200 column families, we have one heavily loaded column family where we actually every week do a major compaction. That particular thing is a very bad design because we didn't know any better. This was, once again, from the playlist cluster, our very first attempt at doing something, and we kind of inadvertently ended up implementing a queue in Cassandra, which turns out to be a very bad idea because, as you hopefully are aware of, deletes are very expensive in Cassandra. Basically, a delete, if you don't know it, is pretty much a write like any other, but with a magical value saying this value has been removed, but it has the same timestamp semantics as all other writes, which means that this so-called tombstone, this magic cookie, will hang around for a very long time. And under some situations, sometimes it's possible for Cassandra to detect all of the different versions of this value that I have, that were there before, that I am a tombstone that says this has been deleted are already gone, so I can actually remove this tombstone. But that's not going to be a very common case. In practice, if you delete data, you will very often end up with having many of your tombstones sticking around more or less permanently. There are, if you search the Cassandra issues, you will find a bunch of very clever optimizations that they have done to find specific cases where they can figure out, no, this tombstone can be deleted. And if you can convince yourself that your data schema fulfills one of those cases, then you can hopefully sleep reasonably well at night. Otherwise, you should worry about tombstones if you're deleting stuff. You can actually convert an SS table to JSON. There's a tool called SS table to JSON or something not very confusing like that, that you can then use in order to find out how many tombstones you have in individual rows. This can be very useful for you if you have bad performance and you don't know why. But for this particular table, we're performing major compactions weekly in order to get rid of these tombstones, because a major compaction is basically the only completely reliable way to get rid of tombstones. And we're doing several 100,000 deletes per month on individual rows in this column family because we hate ourselves. And all other column families that see heavy load are using level compaction. There's actually not a single column family that we have where we can get a performance benefit from use by switching from size tier compaction to level compaction. All right, so right. This is actually exactly what I. This is a different thing though from what I was talking about before. Deletions are bad. Okay. We have one column family where we do a lot of writes. Basically, this is also in the playlist. I don't know if you know this, but the way we've implemented our playlist system is that every playlist is something vaguely similar to a Git repository. It's just a series of patches. You construct a playlist by playing up all of these patches and applying them to an empty repository, and in the end you'll get a playlist. This has some very desirable characteristics, like you can edit your playlists on multiple offline clients simultaneously, and when they come online, they will just perform a transparent merge, and you will get all of your playlist edits fully working. And it's also kind of nice in that you can have collaborative playlist editing with no tension, unlike say Wikipedia. If someone edits an article and another person edits an article, the first person to commit his change will mean that the second person will fail to save his entry. Not so in our playlist system, because we have automatic merging and we're doing cool stuff like that. And it's unfortunately horribly expensive in the database layer. So one of the ways in which this is expensive is that we have people who are using software to write playlists. For instance, people who emulate radio channels using playlists, and they will perform something like one write every 2 or 3 minutes to the playlist system, which ends up being many, many thousands of operations a month. And after a while, we will sometimes see performance in these playlists start to degenerate, and we have the option in that case to simply squash the playlist and delete all of the old changes and replace them with just one snapshot of this is how the playlist looks. And if we do that, what we'll of course end up with is that we will instead have a SS table with 100,000 lines of old data, 100,000 tombstones, and the new actual value, which is the only value we care about. So when we do a squashing operation, performance will go down for a pretty long time, and then performance will come up to basically the same level where it was before by the time we have compacted away most of the data that we overwrote with tombstones. And then it will take many weeks or even a few months sometimes before actually the tombstones also go away, depending on how lucky we are with SS tables and which levels things end up with. So it's not really fixed with level compaction. Level compaction fixes so many of the issues with size tier compaction, but if you're not careful when deleting data, that can still bite you. And if at all possible, you should try and design your database structure so you never actually have to delete the data. All right, so another good performance tip is that if you have data with different lifespans and different write characteristics, don't store it in the same column family. We have one column family where we store various user-specific data. Like for every user we store like, these are the things I'm doing, these are the A/B tests I have, these are my favorite music genres, and so on and so on and so on. Don't ever do that. It's a terrible NumPy pattern, because you will end up with getting lots and lots of compactions because you are writing a lot, but then you will recompact again and again old data which is not actually being changed. So you will be doing lots of users busy work. Also, repairs become that much harder when you have the actual changes spread out over lots of data that doesn't change. So overall, if you have, for instance, a user database and you have some user data that's written to often and some that is rarely written to, put the different things with different lifespans and different column families. That way you will get much nicer performance. And on a very related note, if you have different data with very different popularity, for instance, you have some users that are super famous artists or something, and other users that are just plain old users that no one has ever heard of. Don't try not to put them in the same column family as well, because if you have a small data set of very hot data, you can do a bunch of cool things to that to increase performance for those guys specifically. And that becomes so much harder if that is spread out together with terabytes of very rarely accessed data. So some of the things that you might want to do if you have a very hot data set is perform major compactions specifically on that data. You can use the Twitter method. They actually have a specific Justin Bieber cluster just to handle his tweets. The same thing with Lady Gaga and a bunch of other things. They are calling it Justin Bieber method because they started out using it for Justin Bieber because he was the first person on Twitter to become popular enough to warrant his own specifically named cluster. You can also consider locking your data in RAM if you want to. That is mostly if you're using rotating Rust, which you probably shouldn't these days. But there are a bunch of options basically for things you can do to fine-tune and get better performance out of a small set of very hot data. So don't spread it out together with a bunch of cold data. You'll have a bad time. And the unfortunate truth, you want a good performance out of big data, and this is not specific to Cassandra, this is going to be true whatever you do. You are going to have to design your database schema around your common and costly operations. If you look at how Twitter started out, they pretty much had a relational database, MySQL, with joins and constraints, and everything was super easy and super good and looked very nice. And it scaled pretty well up to a certain point, but SQL has a lot of limitations once you start hitting that point. And after that, they pretty much went over to a system where every single type of operation that they perform has an individual solution. So if you want to read all of your tweets, that's one database that is fine-tuned to only doing that. If you want to read some other guy's tweets, there's a separate solution for that, and so on and so on. Every single operation that you perform has its own database backend, which is geared specifically to solving only that query. So forget all of those nice and useful things like normalized data and not repeating data and so on. You can't have nice things anymore in the big data world. The way we use Cassandra is pretty much, again, a toolbox full of battle-tested, high-quality algorithms that you need to put together yourself in a useful and responsible manner. You have to know what all of these algorithms are and what they do, because if you just throw them together randomly, things will go badly. But if you know what they are and what they mean and what they do, you can do some very cool things with it. One thing, and I'm sorry if this means calling out you and Jonathan because of the, I didn't know I would come right then after you, but this here thing, benchmarks with Cassandra, I have found are kind of useless. This is true for HBase as well. It's probably true for pretty much all of the modern big table thingies. The problem is that when you start using Cassandra, even if you load up with a bunch of data, at the start you will have these performance. And then if you run this thing and have heavy write operations going to that database for 1 or 2 years, you will have these timing-based problems that I was talking about, where because you are writing to the same row over a very long period of time, you will get compactions that are suboptimal, and your data will end up in multiple rows and so on. If you just efficiently, fast load up a bunch of data into Cassandra, it will probably come in a reasonably good state, and you will end up with great performance at the start. And if you have done your homework, it can keep on being great performance. But if you aren't very, very careful, you will probably get significantly lower performance over time. This is not a problem that's specific to Cassandra. There are a bunch of other software, including HBase, that has similar or even worse characteristics. But overall, I would be wary of benchmarks saying product A is wonderful, unless they actually say in the preface that, hey, we actually run this benchmark with a full write load with 100% I/O utilization for at least half a year before we did these tests. And I'm pretty sure that you're going to find that there are no such benchmarks out there. And if I'm wrong about that, Jonathan, please do tell me.
Cassandra's still faster.
All right, but you don't have any proof, do you? But that might still be true. All right, so let's also talk about some of the things that have not become fixed problems, because we have committed a lot of mistakes in the past, and we're trying to rectify some of them. We have also seen a lot of improvements over the years to Cassandra. Level compaction did not exist when we started using Cassandra, for example. So overall, Cassandra moves still at a very rapid pace, and we are seeing a lot of painful edge cases that have hit us in the past keep being removed. I had a very mean presentation about 6 months ago called How Not to Use Cassandra, and I pointed out a bunch of things that had not in the past worked very well with Cassandra, and I was kind of pleased to get an email back from Jonathan pointing out that several of the things that we had a problem with have actually been either fixed or at least improved in later versions. So Cassandra is a rapidly improving product. But deletions are still a major problem. If you have to do them, you have to be very careful, and you should probably do a lot of measuring and trying to find out how many tombstones you actually have and so on. You need to accept that Cassandra is a set of algorithms that will be very fast for some things, and it's just not going to be very suitable for other things. You don't want to store a queue in Cassandra. It's never going to be a very efficient operation. That's just one of many things that you should not do. It will not work well for you, so don't. And another thing that we're finding out is that we've kind of been at the technical or hardware forefront. We were one of the first users to use multi-site Cassandra heavily, so that meant we found out a bunch of problems with that. For a very long time, Cassandra was actually responsible for something like 30 or 40% of all our cross-site traffic over the internet, because it was doing some silly things with TCP, and we had to fix things like that. And now that we are moving into the world of these PCI flash cards, we are finding a cool situation where we're finding lots and lots of new scalability bottlenecks. Basically, all the database products have traditionally been almost completely limited by the availability of IOPS. And once you suddenly have so many IOPS, other things become scalability bottlenecks instead. So, for instance, we can look at this cool slide. This is a very write-intensive cluster. Every night we perform something like 10 million individual writes, and this is a cross-site cluster. So there will, if you perform such very large write bursts, you will be in need of repairs, even if you have painted handoff and all of those things. Some of the rights will actually get lost because there's just too high a load. That means that after every night you will kind of need to run a repair, and since this is using level compaction, it will result in several hundred little SS tables, because with level compaction, you will get one SS table of changes for every SS table that need a repair. So if you have 1 million SS tables, you can, in theory, if you're very unlucky, get 1 million extra SS tables inserted at level 0 thanks to this repair operation. That's a theoretical case that will never actually happen in reality. But as you can see here, something like 500 extra SS tables inserted into level 0 is not unfeasible. And it turns out that compacting away 500 SS tables is a big piece of work. And after a while, we simply couldn't keep up. And so by the time we did the next repair job, we weren't done repairing the old ones, and we started to see a build-up of, after a while, several thousand SS tables in level 0, which was boring for many reasons, mostly because our service stopped working. And we basically had to turn off repair for a while, and then we upgraded to Cassandra 1.2, where they had actually made it possible to do multiple parallel repairs in level 0. This is not something that was usually needed back in the rotating Rust days, because you couldn't handle those amounts of runs anyway. But suddenly when you have infinity IOPS available, that's something that's quite feasible. So this is the type of optimization that you started to need. And you can see here is where we upgraded to Cassandra 1.2, so we could have parallel level 0 compactions going on. And yeah, problem solving, basically. So that's very nice. Okay, I'm actually running on overtime, but I am going to talk a little bit before I start about the future of storage. So this is how the storage layer has traditionally always looked. You have the hardware at the bottom, which is rotating Rust, hard drives, slow chunky things with like something on the order of 100 IOPS available per second. Then you have a transport layer, usually like SCSI or SATA, that is geared towards talking to rotating down Rust. It has this idea of sectors and block and even write sizes and blah blah blah, and it's pretty well mapped on what a piece of hard drive can actually do. On top of that, you have a virtual memory layer and you have a file system layer, which both reside in your operating system, which are also very much geared toward talking to rotating Rust. And then, of course, you have a bunch of applications that are also designed to be fast when talking to hard drives. And a few years ago, we had suddenly this stack where we got SSDs. SSDs at the hardware layer are actually flash storage, but everything on top of that, including the transport layer, is still something that is very much geared towards talking to stable disks. And I know some of you might think, oh, well, the SATA has these extra commands so that you can clear things and make things more efficient with SSDs and so on. And that's pretty much bullshit. It's what I like to call turd polishing. You take something that is completely unsuitable to the task, and you fix one little thing to make it slightly better, but you still end up with something that's crap. Then you have the flash PCI cards. We use ones from a company called Fusion.io, but there are a bunch of other companies that implement them as well, and they are all ridiculously expensive so far. I hope they won't be forever. The cool thing here is that you have the hardware, which is flash. You have the transport layer, which is PCI Express, which is not written with the assumption of anything. It will just give you crazy bandwidth and crazy latency and overall very fast. And then you put the actual flash translation layer in the operating system, in the virtual memory layer, where you have a lot more information about what's actually going on, and you need to be a lot quicker nowadays. This will give you 3 to 4 orders of magnitude higher performance. And I would just like to pause here and talk about how big a difference that is. One single Fusion I/O card will be as fast as a stack of hard drives from the ground floor and up to like the 4th floor of this building. That's how many hard drives you can replace with one single flash card when it comes to available IOs. Another way to look at it is the performance difference between a PlayStation 4 and Super Nintendo. And even in the computing industry, that kind of performance is just pretty much unheard of. It's not something that we get to experience very often, ever. And I find that really cool. So this is obviously the future. A few years from now, the file system and the application layer of all of our Data storage-intensive stacks are going to be geared towards actually reading and writing Flash. And that's obviously going to be cool somehow. Honestly, I don't know how. So this is my representation of what the future looks like, because I don't know exactly what it's going to be, but it's going to be awesome. If we look at the invention of the internet, the first thing people did was take things that they were already doing, like sending mails to each other. And then they did that electronically, just working better because it was faster and cheaper, and that's kind of useful, but it's, I mean, email is not that awesome. But after a few years of people thinking about it and exploring the possibilities, it turns out that the internet is this awesome medium. I mean, it's really, really good for distributing pornography, and so many other awesome use cases. So I don't know what we're going to do with all of these new storage performance things, but I know that it's going to be awesome. So I hope that all of you now feel that storage is something that's really, really cool. And I'm pretty much out of time, but I might have time for a question or two. Also, if you want to find a job, we are always hiring and I have like 4 or 5 positions. I have lots of co-workers, so looking forward to seeing some people working at the Spotify offices as well. Thank you.
У нас есть 5 минут на вопросы, поэтому если у вас есть вопросы, пожалуйста.
So, as far as I understand, you are using level compaction in almost all clusters, or it depends?
Almost all clusters, yes.
And did you see any downsides of this approach in comparison to traditional compaction, default one?
Like I said in my talk, level compaction is a lot slower. You will do a lot more compaction work, but we found that for pretty much all of our use cases, the net change was still positive. We still had higher overall performance by using level compaction. The only exception is the one column family where we are doing regular major compactions.
And what size of SS table do you recommend? In your presentation, you mentioned 5 megabytes per SS table. What are the real numbers?
That is a trade-off, and the larger you make your SS tables, the more compactions you will do, but read performance will be slightly faster. So if you want to optimize for very high read performance, up the size of your SS tables. If you want to have slightly better write performance, lower the size of your SS tables. But it's not going to be a huge difference. We've actually found that it doesn't make that much of a change, the size of your SS tables, less than you would think at least.
But what is the smallest and the largest sizes you are using?
To the best of my knowledge, we move between 5 and 50 megabytes. Like I said at the start, we have a very distributed way of working at the company. I don't actually know about what everyone is doing with Cassandra. There are lots of teams working in different offices all over the world doing different things.
Yes. And my last question is, why do you prefer a solution with many clusters instead of one large cluster or several large clusters?
Now that we have these cool Fusion I/O machines with these very expensive storage things, we will probably move to having some kind of multi-tenant solution, because we kind of have to, because the cards are so expensive. Traditionally, it's very, very nice when something breaks to have service isolation, so that when, for instance, your social networking solution breaks down for the second time this week, you don't also bring down login or something that's actually important. So this kind of service isolation is very important to us. So whenever possible, we try to keep things as separate as possible. And this is something that we do very differently from, say, Google or Facebook. And the reason is that basically we can and they can't, because they earn a couple of cents per user and month. We earn several dollars per user and month, so we have a little bit more leeway when it comes to throwing money at the problem in order to move fast.
Okay, thanks.
Можете задать вопрос по-русски, мы постараемся его перевести, если так будет.
You mentioned that you made some bad decisions in the past. Do you have a plan to fix things and stop hating yourself?
Oh, we have spent many years fixing our past mistakes. I would say that for the most part we are actually at a reasonably good state by now. We have some lingering niggling issues, but for the most part we actually kind of know how to use Cassandra these days, and we are experiencing a lot less pain than we used to. When we started using Cassandra, there was very little information out there on how to design efficient data structures. That's not the case anymore. You guys have no excuse whatsoever to repeat all of the mistakes we made. I have held talks at previous Cassandra conferences, and a bunch of DataStax people have given some very good talks about how to design good data structures. And there are also articles on the web and so on, so there's information out there these days on how to do things like that. We started on 0.7 or 0.6 or something like that, so it was a much more immature product that we saw that had a lot more rough edges than Cassandra does these days as well. That's also true.
There isn't much information about how to fix, how to migrate. That would be good for next presentation. You can share the details, how you fix things.
Migrate between Cassandra versions?
Migrate schema changes.
Doing bad design.
Fair enough. That's actually something that's kind of cool in Cassandra that you can do. You have this model where you are writing things with timestamps, right? This is what makes Cassandra writes independent, that you can write exactly the same write 50 times and nothing will actually happen, nothing will break. Because if you redo an old write with the same timestamp and you have afterwards done a write with a newer timestamp, then the old timestamp version of the data will just never get committed. So what you can actually do in the case of Cassandra when doing these kinds of overwrites is a rape of the entire idea behind Cassandra, but it's very useful. You can just start making all new writes that are into the new database schema, and then you have an offline batch job that will read all of the old data and it will read it together with the old data's timestamps, and it will perform reads and it will override the timestamp and set the original timestamp of the write as the timestamp of the write. And then everything will be all independent and cool, and by the time you have finished your batch job, your new schema will contain all of your data and it will be scot-free. So that's something we have done on occasion, and it's kind of messy and ugly, but it's also insanely useful.
Thank you.
К сожалению, у нас закончилось время для вопросов, мы должны двигаться дальше, поэтому давайте поблагодарим докладчика.